permeability in fluid mechanics and the earth sciences is a measure of the ability of a porous material to allow fluids to pass through it. The permeability of a medium is related to the porosity, but also to the shapes of the pores in the medium and a level of connectedness. Permeability. Permeability is the property of rocks that is an indication of the ability for fluids to flow through rocks. High permeability will allow fluids to move rapidly through rocks. Permeability is affected by the pressure in a rock. The unit of measure is called the Darcy, named after Henry Darcy. Sandstones may vary in permeability from less than 1 to over 50,000 millidarcies. Permeabilities are more commonly in the range of tens to hundreds of millidarcies. A rock with 25% porosity and a permeability of 1 md will not yield a significant flow of water. Such tight rocks are usually artificially stimulated to create permeability and yield a flow. Units. The SI unit for permeability is m2. A practical unit for permeability is the Darcy, or more commonly the millidarcy. The name is in honor to the French engineer Henry Darcy, who first described the flow of water through sand filters for potable water supply. Permeability values for sandstones range typically from a fraction of a Darcy to several Darcies. The unit of cm2 is also sometimes used. Applications. The concept of permeability is of importance in determining the flow characteristics of hydrocarbons in oil and gas reservoirs, and of groundwater in aquifers. For a rock to be considered as an exploitable hydrocarbon reservoir without stimulation, its permeability must be greater than approximately 100 md. Rocks with permeabilities significantly lower than 100 md can form efficient seals. Unconsolidated sands may have permeabilities of over 5,000 md. The concept has also many practical applications outside of geology, for example in chemical engineering. Intrinsic and absolute permeability. The terms intrinsic permeability and absolute permeability states that the permeability value in question is an intensive property, that it is a function of the material structure only, and explicitly distinguishes the value from that of relative permeability. Permeability to gases. Sometimes permeability to gases can be somewhat different than those for liquids in the same media. One difference is attributable to slippage of gas at the interface with the solid when the gas mean free path is comparable to the pore size. See also Canusan diffusion and constrictivity. For example, measurement of permeability through sandstones and shales yielded values from 9.0 x 10⁻19 square meters to 2.4 x 10⁻12 square meters for water and between 1.7 x 10⁻17 square meters to 2.6 x 10⁻12 square meters for nitrogen gas. Gas permeability of reservoir rock and source rock is important in petroleum engineering, when considering the optimal extraction of shale gas, tight gas, or cold methane. Tensor permeability. To model permeability in anisotropic media, a permeability tensor is needed. Pressure can be applied in 3 directions, and for each direction, permeability can be measured in 3 directions, thus leading to a 3x3 tensor. The tensor is realized using a 3x3 matrix being both symmetric and positive definite. The tensor is symmetric by the Onsager reciprocal relations. The tensor is positive definite as the component of the flow parallel to the pressure drop is always in the same direction as the pressure drop. The permeability tensor is always diagonalizable. The eigenvectors will yield the principal directions of flow, meaning the directions where flow is parallel to the pressure drop, and the eigenvalues representing the principal permeabilities. ranges of common intrinsic permeabilities. These values do not depend on the fluid properties. See the table derived from the same source for values of hydraulic conductivity, which are specific to the material through which the fluid is flowing. Source: